Welcome, everyone. So there's been a month's break because in January we had 2 talks instead of 1. So technically we're back on track with new talks. These are talks that are hosted between UKSPS and FMSec. And these are 2 networks that deal with security, one more on the formal side and one general security aspects and privacy. And today we have the pleasure to have François Dupressoir as our speaker. And a lot of you probably know François because of his work in EasyCrypt. And indeed, today he's going to speak about EasyCrypt. More generally, François is a senior lecturer at University of Bristol. And there he serves as the head for the cryptography research group, but is involved also in other works in the department, links to security and other matters. And without further ado, François, thank you for giving the talk, and the floor is yours.
Thanks. Thanks, Joanna. Thanks, everybody, for attending or watching the recording. Yes, I do work on EasyCrypt. And I will talk about EasyCrypt, but I will talk about the bits of EasyCrypt that are not so pleasant. So I won't talk about the details of the technical aspects, which are all pleasant and very beautiful. But I will talk about what we've learned from trying to do things that we shouldn't be doing with it. And that, what I mean by that is that it was not explicitly designed for, but that it happens to be okay at doing. And as part of that, I'll be trying to extract some lessons that we've learned on how to think about cryptographic proofs, how to think about them in the formal setting, and then what we need to do in EasyCrypt in order to make it better at handling the problematic cases. So I'll try to go through that in less than an hour. You can see at the bottom right, I've got 15 slides. That's my usual rate of speaking. So we'll try to get through them. I've got also the Blackboard if we need to get to that level of detail, but really I'll be probably using a whiteboard app instead. And without further ado, I think let's just get started and talk a bit about what we should be talking about, which is what is EasyCrypt. So just a general, very brief introduction to what EasyCrypt is, and then what it does and why it's so scary, and then we'll talk a bit about the things we've done with it. So EasyCrypt, it's an interactive proof assistant for computational security proofs, or really cryptographic security proofs. We haven't used it yet for things that are pure security and don't rely on core cryptographic principles or just high-level security proofs. There are some applications that have been done to privacy preserving primitives, but most of them stopped at the cryptographic game-based notion of privacy, rather than thinking about system privacy and how the whole system was giving some privacy notions. And that's in particular for electronic voting. We just stick to cryptographic notions of privacy. It's designed to reason about black box reductions, so really just reductions which are transforming an instance of one problem into an instance of another problem. And reasoning about the equivalences between those problems. We also happen to be able to deal with simulations, so things that don't transform one instance of a problem into another, but somehow simulate one problem from another. And there's a slight difference there, which I don't think we'll actually get to today, but that's worth mentioning in passing. And it's designed to reason about those black box reductions and simulations as proofs of program equivalence. So really what we're going to do is express the 2 sides of the problem, so the property we want to prove and the reduction and the property of the reduction we define as 2 programs and then prove their equivalence. And the issues we face there is that those are probabilistic programs. So the adversary, the systems we're looking at are sampling random coins along the way. They're not just purely deterministic. And they're open programs. So the adversaries are always universally quantified. We don't have their code. We don't know what they're doing. And we still need to reason about equivalences of programs that include those adversaries. And most of the time, we'll also be abstracting away some of the building blocks. So if you're considering OAEP, for example, as this mode of operation for RSA, it's usually defined as if you have a trapdoor permutation, then you can build a secure encryption scheme on top of it. And that trapdoor permutation is left as a black box. So we don't have the details of how it works. And we should be able to prove that OAEP is secure, whatever trapdoor permutation is used to plug into that black box. So we often have proofs of equivalence between programs where we don't have the whole program yet, but some components might be abstract. And the other difficulty comes from the fact that those equivalences themselves are probabilistic. So we'll have two programs, and we want to show that they're equivalent, except perhaps if some low probability event happens. So typically, we'll use that to capture collisions. So if you want to prove that two systems are equivalent, but one of them prevents non-collisions or collisions in randomness or in ciphertexts or whatever, then you'll end up having a small probability of those two programs not being equivalent. In the same way, you will sometimes have cryptographic failures where the adversary manages somehow to guess the key, which is something that doesn't happen in symbolic settings, and in some of the other analysis settings that you would have in reasoning about probabilistic equivalence. And somehow we'll need to capture those failure events, those events that make the simulation or the equivalence fail in our reductions as well. So those are the reason why it's a bit more difficult than just reasoning about program equivalence. We need to deal with probabilistic programs, so programs that produce distributions of outputs that are open. We don't have all of the components, and the equivalences themselves are probabilistic. So why do we even care about this? So the main reason is cryptographic proofs are hard, and they're hard to write correctly, but they're also hard to check, right? So we typically need as much expertise to check the proofs as you need to write them. And cryptographic proofs tend to be the kind of proofs where you need to trust them, right? It's not just enough that the community as a whole trusts them, but it's important to be able to convince non-experts that their data is being handled securely or is handled by a system that provides them with a particular level of confidentiality or integrity. Most of the time, this is deferred to a standard committee or to a government agency like NIST. But sometimes where the fear is that the government or that standard agency might be not so trustworthy, then you might want more independently verifiable evidence. And that's typically those proofs. But again, if verifying the proof requires to trust an expert, then that is a bad situation to be in. So the bright idea that was had in 2009 with the precursor of EasyCrypt, that was EasyCrypt, was to make cryptographic proofs even harder than they are, right? So the idea is you make them harder to write, but they're harder to write because you're essentially explaining it to a very stupid 2-year-old, which is your computer with a reasoning engine that checks painstakingly that each of the steps of your proof are correct. And that checking itself is automated. That doesn't solve all problems, right? So you know now that the proof is correct as long as you trust the tool. So there's a bit of trust that's been pushed away into a smaller component, but also there's still trust in the security definition, right? So you know that the proof is not wrong, but you don't know that the proof is of a result you care about. And so all of the things I'll be talking about now are in the context where we believe the definitions, and I'll be mentioning a couple of places where that may be a mistake, but where really our main focus is, can we get the proof right in a reasonable amount of time? So how much harder are we making it to write the proof? And still get reasonable results in terms of verifiability and completeness. So are there things that we can't prove at all? And how do we do this? Well, EasyCrypt is not easy. So this is the slide where I explain exactly how much harder we make it. So in order to formalize a proof in EasyCrypt, you'll be interacting with all of these things. So you'll be interacting with 2 programming languages, a small polymorphic lambda calculus, which is used to essentially formalize mathematics and the core component, the core constructions, the core data types that you will be manipulating. So if you want lists, the library is written in this. If you want to describe a new distribution, it's going to be written in that language. If you want to describe a finite map or a set or anything like this, we have libraries that are written entirely in that small polymorphic lambda calculus that specify mathematical operations and simple data structures. And then on top of that, we have a probabilistic while language, so a small imperative language where you have procedure calls and probabilistic sampling, so sampling from distributions, that we can use to describe algorithms, to describe reductions, to describe adversaries, to describe oracles, experiments, all the games, and all the things that make cryptographic security definitions expressible in a sense. And that's wrapped inside a module system, which allows us to specifically say, I want a construction that's parameterized by another set of programs. So when I was taking the example of OAEP, that's parameterized by a trapdoor permutation, we can literally say OAEP applied to a trapdoor permutation or parameterized by a trapdoor permutation is going to be this piece of code, which sometimes we'll call an oracle or one of the procedures that's provided by the trapdoor permutation. So once we've defined all those objects in those programming languages, we can start reasoning about them. And for that, we've got a whole bunch of logics. So I have 4+. I think I list 6 on the slide there. There are more coming and more being developed all the time. So there's a possibilistic whole logic, which those of you from formal methods will know about. So that allows you to prove partial correctness properties, where you say, whenever this program terminates, a particular property holds on the final state. And all you know is that all reachable states have this property. We have a probabilistic whole logic, which now allows us to show termination on one side, which is an important property to have when you're dealing with cryptographic reductions, but also probability of particular events. So if you want to bound the probability of a collision happening, then you'll be using probabilistic whole logic rather than just a whole logic that says collisions sometimes happen. This is one of the things you could prove. The probabilistic whole logic allows you to say collisions happen with a probability that's less than q squared over the size of the set you're sampling from, for example. And then we've got the main logic, which we use for the cryptographic proof, which is allowing us to reason about equivalences between programs, and that's a probabilistic relational whole logic. And I won't go into the details of all of them. All of those 3 logics, they are essentially wrapped inside what we call the ambient logic. So they float around in that ambient logic. And that ambient logic is essentially a higher order logic. So you can quantify over predicates. And it's literally just higher order logic as you would find it in Isabelle Hall. Plus, additionally, some additional terms that allow us to embed judgments in the other logic as formulas of a higher order logic. So it's entirely possible for us to write statements of the form, if those 2 procedures are equivalent, then these 2 other procedures are also equivalent. And so we can we have this embedding of all those logical judgments into our ambient logic. And on top of that, we have now logic for cost. So we can prove some facts about the cost of a reduction or of simulation. There is logic for the expectation of particular events, which is simpler than the probabilistic whole logic, but gives you slightly less. And we've got others coming along as well that will improve usability of the tool. And all of those, essentially, the 4 that I mentioned explicitly there, are things that we manipulate and we use in every single proof we do. The other ones, depending on the formalism, on the precise formalism that you want to use, you might use them or you might not. But they're typically there for you to use if you want. And then on top of that, again, we've got 2 meta languages. So one is the language of theories, in which you can wrap entire sets of declarations, definitions, and proofs. And then you can later instantiate them to concrete types or concrete variables, concrete values. So most of the time, we'll do reasoning where we assume an abstract type of keys, for example, with some abstract distribution over that set, over that type. And then when it gets to it, when we want to prove something about a concrete instantiation of that proof, we'll say, okay, well, now the type of keys is actually bit strings of like 128 bits or 256 bits, and the distribution of the keys is the uniform distribution over that type. And then we can then just refine and instantiate an existing proof to a variety of instances in order to get several proofs out of a single complex one. This is also something we'll be using. We use a lot to instantiate generic cryptographic arguments, and I'll be saying a bit more about that later on. The second meta language that you will need to deal with if you start an EasyCrypt proof is then the tactics language. So that's literally the language of proofs themselves, the language you use to drive the proof engine. So it's again a programming language, but the program you write is essentially one that creates another program that happens to be a proof. Don't worry about it. So you'll be writing proofs that say, okay, I want to apply this lemma, or I want to rewrite a particular equality in order to make progress in the goal, in the proof. And that language, for those of you again from the formal methods side, is inspired by SSReflect, but with a much simpler type system. So we're not using dependent types or logical formula again, or higher order logic plus a couple more extensions, but they're not complex objects. So we've got a much simpler proof language, which gives much more verbose specifications sometimes, but also much more intelligible than things that have hidden facts inside types and all those things. So that's a quick presentation of what EasyCrypt inflicts on you when you try to use it, and a big question of why does it do this? Why is it designed that way? And the main reason why it has that level of complexity is that complexity is required if you want flexibility. If you want a tool that is able to tackle primitives, constructions, and protocols, then you need to be able to you need flexibility to express security at all those levels and to express the constructions at all those levels as well. And that means that EasyCrypt as a tool and as a set of languages has to be more complex than tools that focus specifically on constructions like SSProve or FStar, or tools that focus entirely on protocols like CryptoVerif or Squirrel. And so we really need all of that and that level of complexity in order to span all three levels of the primitive to protocol hierarchy. And indeed, we have that flexibility. So we can do proofs for primitives. So we have proof for SHA-3. We now have a proof for XMSS that should become public in a minute now. I have a proof for XASA20. There are proofs for CBC, CMAC, Poly 1305, a whole bunch of crypto constructions, including some that are very recent, like Saber and Dilithium. And all of those are formalized in EasyCrypt as they are, not just abstractions of them, but really the concrete instances that are being standardized or have been standardized are the objects on which we have EasyCrypt proofs. And there are difficulties that are involved in that, and I'll be discussing them. That the whole point of the talk is to discuss them and what we've learned from them. We can, much more easily than for primitives, get proofs for constructions as well. So we can get a proof of composition for Cha-Cha and Cha-Cha Poly, for example. And this is done generically as if you have a stream cipher and a one-time MAC, then you can get a proof for their generic composition as is done in Cha-Cha Poly, and then you instantiate it to Cha-Cha and Poly 1305. We've got a proof for MAC then encoded and encrypted CBC mode, which was the TLS 1.2 record layer. And again, this is done generically, composing a proof of CBC with a proof of unforgeability for a MAC, just by a generic composition result. We have, from last year, a proof for CryptoBox, which is this publicly authenticated encryption that's used in SALT. We've got proofs for voting, and I'll explain why that's a construction and not a protocol. And we've got proofs for Amazon Web Services key management service, so the AWS KMS. And that's, again, a very big construction, but it's still construction proof. OAP, PSS, a whole bunch of simple constructions that we have generic proofs for, and then instantiating them down to concrete instances. And so those are very nice as construction proofs. But again, they're not the be-all end-all of cryptography. And what we really want is start thinking about interactive protocols as well. So we have historically obtained proofs for authenticated key exchange. So there were proofs for Naxos invariants. They have been lost to history. The repository that contained them have disappeared, and we don't know where they are. But there are publications attached to them. They just don't tell you how they were formalized. So we've got ongoing efforts to try and do them again, but better. So applying some of the lessons we've learned and that I'll be talking about today. With Joanna and Katalin, we have a proof for a distance bounding protocol. And this one was interesting because the main difficulty in that protocol was actually the interactivity and not the crypto at all. The cryptography was dealt with just with a single part at the start. And then the difficulty was interactivity and the physical model of the time it takes for a message to travel. And I'll hopefully take the time to discuss that, although I'm keeping an eye on the time and I'm not doing very well. And there, again, some privacy preserving primitives like private information retrieval. And again, those are interactive protocols which add their own layer of difficulty in some ways, but make it easier in others. And and those are really the three layers of cryptography and cryptographic proofs that we've done in EasyCrypt that cover pretty much the whole of cryptography, as long as you're happy with black box reductions. And each of them has characteristics that I'll be, and problems that arise that I'll be going through in a minute. And then other reason why you might want to use EasyCrypt, I'll just skip over that one, you can read it. But so using EasyCrypt in these three different settings is not always pleasant. And this talk is exactly about what we can learn from those unpleasant times we have. You can see how unpleasant they were by the amount of hair I've lost over the last 3 years, maybe 10, I don't know. I'm older than I think. And hopefully I'll be, with this talk, helping you avoid this by giving you hints as to what you need to look out for if you start using it. So let's start with primitives. So that first layer here is primitives, and they are really things that are self-contained. They're very small components in general. Like their description is not very large, but their proofs are actually quite complicated in the end. One characteristic is that they're self-contained. They don't have, that's not entirely true. You can usually describe them as self-contained, even if sometimes you will be assuming some ideal core in them. So SHA-3, for example, we're not going to prove anything about the permutation inside, but we can prove that if that permutation was ideal, then SHA-3 doesn't introduce additional vulnerabilities that would not exist in that core. But it's still a primitive proof rather than a construction proof in my book anyway. So the lessons we learned from formalizing primitives, and I think this story I'll skip and I'll give you the next one. So the three problems that we face are that the mathematical arguments that are deployed typically at primitive level are complex. They're very, very hard. So deep algebra, so you'll be relying on the specific instance of a mathematical construction, or you'll be relying on complex discrete arguments. So just part of the story time in the SHA-3 proof, as part of the proof for SHA-3, the simulator is essentially constructing a graph of all the queries that the adversary has made to the oracles. And even formalizing this notion of graph turns out to be a nightmare. And so formalizing it and then proving something about it is just really, really hard just by itself. So it's a very small construction, but the proof for it requires formalizing a whole bunch of things that you typically wouldn't think about when you're formalizing a standard crypto proof, and in particular when you're formalizing a proof for a construction. Some of those primitives, when you're doing the proof for them, require you to reason about the distributions that are produced, rather than what EasyCrypt typically prefers to do, which is reasoning about the processes that produce that distribution. So typically what we do in EasyCrypt is we look at two programs and we prove that they're equivalent. So we prove that they produce the same distribution by proving that they literally in lockstep do the same operations or do operations that are indistinguishable. But when you're looking at primitives, sometimes you literally want to show that this complex program is producing a distribution that is uniform over an element. And so you want to show that it simulates uniform sampling in a particular set. And then you no longer have a process that produces the distribution. You just have, I sample uniformly at random in a set. And now you suddenly need to talk about the distribution that's produced. And that's something that's really, really difficult to do when you have a program that describes the distribution. And so the idea is there to lift directly the reasoning explicitly to the level of distribution. So come up with an expression in that polymorphic lambda calculus I was talking about that describes the distribution as opposed to describe how it's constructed, and then simplify it and hack away at it until it's reduced down to, yes, it is the uniform distribution over that set. But all those transformations are things that are quite difficult to do, and perhaps because of the fact that we have a very simple logic as opposed to quite an expressive one like SS reflect would have. And the third problem that we face, which is more not a problem with the proof itself, but a problem about what we want to do with it once we have it, is that those primitive proofs, they need contextualize. So it's fine to say, okay, I've proved this object, I've proved this statement, I've defined an object and then proved something about it. But if you've defined the object and the security property that you're proving about it in a way that is incompatible with every single thing that could use that object in the end, then you've made your life harder, not easier, right? So those primitive proofs, they're hard by themselves, but then you also need to think about how will I connect them to proofs for objects that use that primitive in the end. And I'll be opening that up a little bit more when I talk about construction. So with all those problems in mind, and with all the primitives that we've actually formalized, so all those, what have we learned? How do we make our lives easier for formalizing proofs? And I'm going to emulate Balmer, except possibly and hopefully a bit less sweaty. And I'll say, what you need to think about is generalize, generalize, generalize. So prove families of primitives at a time. Don't just prove one primitive. If you have a sponge construction, you can apply a proof for your sponge construction to all possible sponge-based hashes at the same time, or all possible sponge-based constructions at the same time, as long as you identify the right primitive and you generalize in the right ways. So we haven't done that yet, but that's an interesting thing for somebody who's thinking about getting into EasyCrypt to think about. And things that you can generalize over the size of the sets, over the number of iterations you do, over the key distribution. Most of the time, you don't need to know in your proof that your distribution is uniform. You don't need to know that all keys are in your distribution. And there's lots and lots of constructions where actually the key generation algorithm will not sample some keys, will not produce some keys. And so if you do a proof that assumes a uniform distribution over the whole set of keys, you end up having to finesse your instantiation as opposed to just generalizing your proof and instantiating it as it is. So there's quite a few lessons to be learned there about generalizing in the right ways and really assuming only the minimum things that you need for the proof. This is easier to do when you have a tool that tells you whether your proof is valid or not, because you can just start from nothing. And then as you do your proof, figure out, ooh, I need this fact, and just go ahead and add it after you've convinced yourself that it's fine to assume. So this generalization it's a hard thing to do, and it comes with having done more than one proof. But it is really, really useful to think about proofs more generally and the objects on which you do the proof more generally than what's on paper. The second Balmer-like lesson is modularize, modularize, modularize. Even if you have a primitive, it looks like a monolith, right? And I described it as the small core component that's really the core of everything that you build in cryptography. But even there, you want to decompose it as much as possible. Your primitive is dealing with padding, modularize it away, right? Say, I've got a core that deals only with padded strings or with padded inputs, and then padding is just a layer on top that can be done generically. And again, this is where you generalize. You can easily prove if I've got a secure construction for padded inputs, then as long as I've got injective padding, then or whatever property you need on your padding to make the property hold, then adding padding is not going to break security, right? As long as your padding is not done stupidly. And so decomposing that means that when you're focusing on this complex hard argument at the core of it, you no longer need to worry about how does that interact with padding. When you need, so both of those examples are taken from the SHA-3 proof, where padding on the input is actually a massive distraction from building that graph, which doesn't actually look at the padding at all. The graph I was talking about. And then the iterated application for more output, it's also from the SHA-3 proof, where the core construction is just producing one chunk of output. But then for the SHA-3 construction as a whole, and for the Schenck construction, what happens is you then run it again with longer inputs, and that gives you the next chunk, the next block of output. And this iterated construction, you can deal with it modularly as well. You can say, well, if I've got a core component that is secure, just producing one block of output, then I can always construct the one that produces more blocks of output using only the security of this one, and then prove that that construction is also secure. And one important lesson that we got from being able to do that was to embrace nonsense, right? So this particular construction where I was layering, so you've got this core sponge that produces one block of output. And then you iterate it on longer input to get the next block of output. That's essentially how we iteratively construct it. But if you do it this way, then that construction is going to redo all of the intermediate processing all the time. And in fact, all of that intermediate processing, if you're not careful about the way you express your final result, you end up having a reduction or a simulation that has quadratic complexity in the size of the problem, or in the number of blocks that you're producing. And from the point of view of tightness of the security proof, this is bad. This is horrendously bad. It means that you would need a SHA-3 construction whose block size is twice as large in order to get the same level of security if you take only that proof. And so the idea is, in intermediate steps of the proof, and in particular when you're layering, it's fine to have things that are less optimal or things that are nonsensical entirely as standalone security notions, as long as you take this final step that gets rid of it in the end. So in this case, once you've got this layered construction that says I'm producing one block at a time, and then iterating with a slightly longer input to get the next block, and then iterating again with a slightly longer input to get the next block. You've got this construction, it's inefficient, it's suboptimal, but you can prove it very easily, equivalent to the construction that doesn't redo all the prefix computation and just outputs the next block each time. And this was freeing, being able to do that and having the flexibility to do that. Again, this comes back to the flexibility of the language. Being able to say, we're going to modularly build an inefficient reduction and then prove that it's equivalent to an efficient one, which is the one we want, was really, really, really freeing in terms of understanding the proof, building it, formalizing it, and convincing people that it made sense. So that was quite good. And so the lesson here is extract, generality, and abstract, modularize. So extract generality and generic reasoning principles, abstract away the things you don't need. And I think also abstract away your idea of what makes sense as a security notion and as a valid proof step, essentially. As long as it's useful to make progress in the proof, it's a valid proof step. You don't need it to make sense as a standalone notion. Another very simple example of place where sometimes an intermediate proof step doesn't make sense. In the proof of security for PSS, so that's a signature scheme that's essentially based on RSA as it's standardized. The proof essentially says, so as part of the proof, you need to simulate the operation of assigning oracle without having access to the secret key. And the way this is done is by sampling the output, so sampling a signature, and then inverting it back into the message that would have produced that signature. And the problem with doing it that way is that sometimes you sample a signature where when you extract the message from it, you end up with something that is not well padded, that would not be ever a valid input for that signature scheme. And so what you end up doing is rejection sampling. So you sample a signature and then invert it back into a message, which only uses the public key. And then if that message is not actually well padded, you sample again and go back and forth and keep doing it that way. The problem with this, so this is beautiful. This is quite a nice proof. But the issue is that this reduction, if you use it as your final reduction, it's not polynomial time, right? It could go on forever. So it's only expected polynomial time. But if you try to immediately build a polynomial time reduction for that, you would be there for years trying to formalize it. Whereas just doing a rejection sampling, accepting that sometimes it's going to take a bit longer than poly time, and then saying, if it does, I'm going to cut it and accept that my simulation will not be perfect and sometimes will fail, then you immediately again free yourself. So you take a nonsensical intermediate step and then take a step that makes it make sense again. And that's really freeing again, and is the thing that gives you those generic reasoning principles. And that's really, really useful to get to. So that's it for primitives. The main thing is, as soon as you've got something that you look like a proof principle that looks like it can be reused, abstract it away, make it a library. Even if you don't contribute it to EasyCrypt, keep it in your pocket. It'll be useful again next time. And then we can move on to constructions. And the main lesson from formalizing construction is that they are easy, right? They are relatively, well, easy-ish, right? As the title says. So typically, the hard math that I was talking about in terms of formalizing primitives, all of that is hidden away under the construction. So again, you'll have the construction which is parameterized by the thing where the hard math is hidden. And that's not always true. So Sarah can attest to Diffie-Hellman-based signatures, sometimes doing some of the hard math as well. Anything lattice-based, currently we don't have good abstractions over lattices. And so there's always going to be a bit of bleeding from the hard math into the proof for the construction. But typically we can deal with that and deal with it in somewhat abstract ways. We just don't have much experience of dealing with them yet. But as we build up our libraries, we'll probably be finding the right abstractions to think about this thing. There is, however, a problem that comes from doing construction proofs, in that when again, the principle of the construction, and I think I skipped this bit here, principle of a construction is that you have an algorithm that's parameterized by a primitive, and that constructs up a new construction, right? A new security functionality. And the problem is finding a model in which to do this proof. So if you do this proof in the standard model, so just the adversary has access to oracles that provide inputs and to which they provide input and get outputs, then you have a nice proof that says for every primitive that achieves whatever notion of security you assumed, the construction you get by applying the construction to this primitive achieves some other notion of security. But what happens then if you pick a primitive that requires a random oracle, right? That models that for which the security proof requires the adversary to have access to a random oracle, or models hash functions as random oracles, or some other idealized model, some other trusted setup or idealized model. So you do your proof in the standard model, you instantiate it with a primitive that's that requires a random oracle, for example, for its proof. And now all of a sudden, this construction that you've got, the security notion for it has to also expose that random oracle to the adversary. And so your entire proof becomes typically entirely useless, and you need to redo it entirely with the random oracle exposed. And so all of that is like deciding whether to do a proof in the standard model and then redoing it if you instantiate with a random oracle or some other trusted setup. Or conversely, doing the proof always assuming a trusted setup, and then just removing the trusted setup if you don't need it. This is a difficult decision to make, and I'll be hinting at some ways in which we could deal with it, but that are not completely perfect. And so both of them have issues. One of them, you need to redo your entire proof, and typically it's tedious, and you don't learn anything by doing it. And anybody can ask Catalin exactly how that feels. And on the other hand, you do a generic proof where you always assume a trusted setup, and then you remove it. But then you need to convince people that this is the right proof, that the proof you gave them is actually the one they wanted. The one they want is not the one with a random oracle. They just want one that works, and that is intelligible, that recognizable as the notion of security they care about. And so that's not an easy choice, but that's more of a social question rather than a proof question. And so let's move on to lesson. And the last lesson is exactly about this, about how we can deal with the social question technically. So from the lessons on constructions, generalization, modularization will help you. The main issue with applying generalization, modularization to constructions is very often you need to come up with a whole new proof. You can't just formalize an existing one, because the existing ones will not abstract away. They will go through abstraction layers willy-nilly, just say, ooh, I know that the mathematical structure that's underneath it is exactly this lattice-based construction, or exactly this lattice-based operation, and so I can use some fact about it up here in my construction proof. And this is where we need to do more learning, right? In terms of we as a crypto community, no longer as the EasyCrypt community, we need to learn more about how to write proofs that are easy to formalize, and how to make them how to properly isolate irrelevant details. A lesson here is viewing everything as indistinguishability in terms of proofs for constructions is really, really useful. EasyCrypt is really good at proving equivalences. Write everything as an equivalence. Every single property you can, write it as an equivalence. Generic arguments, all of those that you got from formalizing primitives, all of those are really useful again for constructions. So once you've got your primitive transformations or arguments that are generic, you can always use them at all layers. And in particular, it's really useful here, except for the fact that sometimes it's still easier to replay the argument by changing some of the details than it is to actually just instantiate them and apply them. And so we need much better support for instantiation of generic arguments. And then this last problem that I was talking about picking a model in which to do the proof for the construction so that it can be lifted to random oracle model. This is possible to do, but it's very ad hoc. So for each construction, you'll need to do that lifting separately and independently from all the other ones. And the main issue there comes from the fact that that lifting essentially needs to be parameterized by what oracles are being exposed to the adversary. And we can't do that in EasyCrypt at the moment. We have to do it. All those proofs that turn a reduction into another reduction, we need to specify exactly what the problems we're reducing are in terms of what oracles are exposed to the adversary. And so we need better support for meta reasoning over modules and for reasoning about, essentially it's meta reductions, right? So that's a very useful crypto proof technique that we don't support, and the only way in which we can support it is essentially by replaying an existing generic proof that will give us nice results. Apologies for this. I thought I turned it off. So let me quickly skip through formalizing protocols. The main lesson is don't do it at the moment. So the two big problems that we face is that EasyCrypt's model of computation is entirely sequential. We've got one main thread of computation. The adversary at some point takes over after some initial setup, and then controls the execution of oracles and schedules them and schedules message delivery and all of this. Whereas protocol security specification are often phrased, at least, in concurrent settings. So you'll have several parties running in parallel and some network that delivers messages in the middle and might be controlled by the adversary. And in order to capture those proofs, or those even just the security notions, means encoding that concurrent execution setting into the EasyCrypt model, giving the adversary explicitly access and control over message delivery, message passing, scheduling, all those things. And then if we encode that into the EasyCrypt model, that means we need to deal with it explicitly in the proof as well. We have no way of saying, oh, but it's fine, all of this is concurrent, but it's fine because there's this generic argument that we can apply that tells us all of this is good. So this is one issue, and I don't know how to deal with that one. The second problem is that most protocol security notions are completely unintelligible if you're trying to make sense of them formally. As a simple example, in authenticated key exchange notions, which are the ones that are fresh in my mind at the moment, so what you want is usually to prove that two instances of the protocol, one initiator and one responder, will agree on the final value of their key. No other instance will agree on the final value of their key. And also, nobody else will know the final value of their key or will be able to distinguish it from a random bit string. But all of that is expressed in terms of a freshness condition that says, for each instance, whether it's fresh or not. And only fresh instances should have this benefit of confidentiality. But if you're looking at it, that freshness condition actually also embeds in it the authentication breaks, the fact that authentication breaks are impossible, by essentially saying if an authentication breaks happened, if three instances now believe that they're talking to each other, then will essentially force a confidentiality break so that the adversary will win. And all of that is so hidden that it's really difficult to interpret what the authenticated key exchange notion actually tells you. And it's also very, very tricky to interpret it formally as an EasyCrypt proof and as an EasyCrypt model. And again, this is a point, just like in the constructions, generalizing and modularizing a proof often requires an entirely new proof. Doing that for protocol security at the moment looks like it's going to require coming up with new definitions of security and proving them equivalent to the existing ones. And this is obviously a big problem because it's going to require a lot more work than just saying we've formalized something that exists and something that a security notion that has convinced cryptographers of its usefulness. So again, at the moment, don't try and use EasyCrypt on protocols. We are working on understanding better how that works. But there are some things that we've learned, and so I'll talk briefly about them. The first thing is often formalizing protocol proofs goes idealize the cryptography, and then you're left with the hard and tedious bit, which is dealing with all of that concurrency and interaction. And all of that is exactly what symbolic verification is doing very well. And so what we should be working on, one of the things we should be working on, is better connections between EasyCrypt or other machine-checked cryptographic proof tools and symbolic reasoning tools, so that we can use one to idealize the cryptography, deal with all the computational parts, and then symbolically reason about the non-computational parts, so all of the scheduling and symbolic issues that could arise. And the second point is really there is a lot of definitional work to do if we are to try and formalize real-world protocols from top to bottom. So if all we're interested in is looking just at an authenticated key exchange protocol, then formalizing the existing notion on an existing protocol is going to be fine. But if we want to formalize the AKE protocol and then compose it with a proof for a construction, then compose below that a proof for a primitive, then we can't do this with the existing notions. It's just not going to work. And so we need to find the right ways of expressing protocol security at the top level in order to be able to do this top to bottom construction of a proof that is then machine checked. And that's pretty much the end of my detailed lessons. Some of the other lessons we've learned are more for us than for you, except actually the first one is for us more than for you. We need more beginner-friendly material and more support for that. But how we're going to get there is by getting more users. And again, ideally, you'll be looking, if you're thinking about EasyCrypt, you'll be looking at doing proofs for construction. That's really the sweet spot where it's really good. And it needs more developers. So if you are formally minded and you want to do to support this effort, then let me know. We need more people who write code and libraries and do all those things. So you're welcome to contact me. My email address is on the first slides and on the title slide. And yeah, just drop me an email. We can get you in. Thanks.
Right. Thank you. Thank you for what was not a very formal heavy talk, but a very informative talk. I'll open the question to the floor to questions. If anyone has questions, please go ahead. Okay, no question. Then I have a question. So if you go back to your original slide in which you said about all the logics and how they're all needed and how they're all really sort of embedded into this well, they're embedded into whole logic, but how they're all wrapped into the ambient logic. Do you think that now with doing proofs the way you're doing this could be done differently? Do you think that there would be another way to do these proofs, maybe more complicated, but directly on the probabilistic relation whole logic? Or do you think that the ambient logic is needed entirely?
The ambient logic is needed because that's where we prove the mathematical results. Right, so the ambient logic is the one that we use to prove, to literally prove everything about the data structures, about lists, all those things. We need lemmas and libraries of lemmas, so that can later be used in proofs for programs. And all of those are written in that ambient logic. Whether we need the embedding or not, that is a good question. At some level, we do, in the sense that most of the time, what you end up proving in terms of result is for all adversary, so that's quantification over a module, over a p-while program. So for all adversary, that makes at most Q queries to an oracle. And that makes at most Q queries to an oracle is actually a judgment in whole logic. Or for all adversary that terminates with probability 1. That's also something that we have to assume very regularly. So for all adversary that always terminates. And that's again embedding inside the statement inside the theorem statement. We need a way of embedding this this probabilistic whole logic that expresses terminates with probability 1 inside a bigger security statement that says that the reduction is correct for that adversary. That the advantage of the reduction is bounded by the advantage of the original adversary, the right way around. And so, is there a simpler way of doing it than having this embedding of logic? Probably, but is going to obfuscate a bit the statement. So one of the big principles that we had at the start of EasyCrypt was to not obfuscate too much, so that the statement was intelligible and didn't hide too much stuff away. so that a cryptographer looking at just the top level file that says this is what we prove would have the full definition of the construction, the full definition of the reduction, full definition of the assumptions and the security goal, and then a theorem that says this is what the result is. And if you don't have this embedding, then you start hiding things behind keywords and other details. So I think we want to keep that, all of those logics, and we want to keep the embedding. The embedding doesn't really make it more complex. It's just having to deal with all of them, because just each proof that you do, you have to deal with possibilistic, not always possibilistic, but at the very least probabilistic and probabilistic relational, or something that will always pop up in all the proofs that you do.
Okay. I have another question, but maybe someone else has a question. This makes a lot of sense, what you just said, by the way. And it explains why you need it. Yeah, and why you can't get rid of the embedding. Thank you. Kathleen is lit up.
Sorry, I was trying to. Sorry, first of all, can you hear me?
Yeah.
Perfect. Sometimes I have issues with my microphone. I was trying to find the raise your hand button. Okay. So I think you did scare a lot of people with EasyCrypt. And so do you have some good advice to motivate people to actually start using it?
Yeah, it's great for construction. So it's if you're thinking, so and actually even some primitives that are actually construction. So I listed. Sorry, let me scroll properly. I listed a few here. So SHA-3, don't look at it. This is a primitive that's a proper primitive. XMSS, same thing. It's a primitive that's a proper primitive. The proof for it is a massive engineering effort. XSASA 20, it's a relatively easy proof, and it's really elegant. And it's actually more of a construction proof in a sense. So it looks like a primitive, but it's actually a construction, and it's quite neat as a starting point. And again, one of the big things, maybe this is a good lesson that I should be listing as well. XSASA 20 was a pleasure to formalize. I did it in about 8 hours. So it would probably take a beginner a bit longer than that. But it was a pleasure to formalize because the paper proof by Bernstein is actually doing all those things that I was talking about. It is doing the generalizing and the modularizing for you, so you don't have to do it. He very clearly identifies, on this type, we assume finiteness, right? This set has to be finite, and we need a uniform distribution on it. That set doesn't have to be finite, and so you immediately know that you don't need to assume finiteness on it. And the reduction is explained very clearly. The proof is explained very clearly, and I think this is really another lesson, I guess, is if the proof is written well on paper, then it's going to be easy to formalize. If the proof you start from is not written well, which is unfortunately most crypto proofs, then it will be hard to formalize. But most of that work will not be because of EasyCrypt. It will be in understanding the proof in the first place. That goes back to the point of proofs are hard to write, and they're equally hard to read. And that's something that is even more salient when you're making the proof harder to write even. So XSASA 20, do try to take a stab at formalizing it if you're thinking of starting with EasyCrypt. And then the other ones listed here again are complex mathematically. But other than that, look at constructions, right? So XSASA 20, very good starting project. Chachapoly, generic modes of composition for authenticated encryption. Very, very nice to look at. All generic constructions will be a pleasure to look at and formalize. So look at those as my advice.
I have a final question before we switch to one. So obviously I forgot to say thank you for the presentation. Very interesting. I think one of the things that, so I do have experience with voting, so I can estimate how long it would take to run and prove something in EasyCrypt. And I think 1 year of effort, it's approximately as an average. How would you estimate for the other constructions was there kind of on the same line, were more challenging? I mean, ignoring the fact if you have a proof, in fact, then obviously it's very easy to follow. But if you have a sketch of a proof, which most of the construction have.
So Chachapoli was a lot of work, but again, they had to formalize polynomials. They had to formalize the security property for poly 1305 and the proof for it. And after that, it was 2 weeks of effort. KMS, that's the biggest one. It took about a year of formalization, but that's a very big construction. MECBC was about 2 weeks of formalization work. Starting from a proof of CBC, if we'd had to formalize the proof of CBC, it would have been another week and a half, I guess. Those are person weeks, not just straight weeks. I need to sleep sometimes. So again, voting, it's one of the larger constructions. That's, you know, I mentioned that I would discuss why it's not a protocol, and I didn't. The reason I don't consider it a protocol is because most of the models don't actually model interaction as a concurrent program, like in a concurrent setting, and that's really my distinction between constructions and protocols. But yeah, it's really a protocol in terms of size and complexity of the beefiness of the description, really, of the definition. But in terms of security model and the kinds of issues you have to face in formalizing the proof, it's more of a construction. But because it's so beefy, I think it skews towards more time spent formalizing it. But now that you've done it in 1 year, how long would it take you to formalize the next voting protocol?
So personally, I think it would take me less. Unfortunately, I have less time than I initially had.
Yeah, but again, I think it's more like start with small constructions, CryptoBox, secret CryptoBox. We haven't formalized it. It's, I guess Chachapoli is it. But there's interesting things to do in generic ways that are only done on concrete instances at the moment. That would be nice to just generalize and abstract and modularize, as I described. So loads of starting points. Joanna, you had another question.
I do, and this is more of a philosophic question, maybe. So, you know how a lot of the difficulty in EasyCrypt is to do with interaction. You even said it yourself. Mm-hmm. And you know how, you know, for very simple things, I'm just going to use the story example, you can get something like a non-interactive zero knowledge out of a Sigma protocol or something like this. Is there any hope that, in fact, what you could do for some constructions, instead of doing a proof on an interactive system, first you reduce this system to a non-interactive system with some proof of said reduction, that it preserves certain security properties, and then do a proof on what's left, that is a computational proof on the non-interactive construction left out of the interaction?
In a sense, that is what we do for voting, except we don't formalize the first bit of the proof. We trust
the first reduction.
We
yes.
trust that Bogdan and Veronique didn't mess it up, and then that it doesn't get messed up when we fiddle with the definition of the non-interactive version. But in a sense, that is what is done for that setting. That is what is done for most of the KMS, the key management service. It is actually a massive interactive system, but they did a lot of paperwork to down to a non-interactive description, a non-interactive security notion.
Okay. So none of the interactivity in there is formalized, much as you know, we had our own issues. So in there also, it's all eluded or whatever, foregone. Yeah. Okay.
So there's yeah, but again, there are interesting questions there that are less EasyCrypty and more, how do you define security? That would be nice to look at. So would it be easier and more trustworthy in a sense, because you wouldn't have this trusted component that reduces interactive security down to non-interactive one? would it be easier to just bite the bullet of dealing with non-interactivity with interactivity in EasyCrypt and formalize that proof instead of having to wrap your head around the AKE notions I was just talking about. The whole thing about those freshness conditions is to avoid in the pen and paper proof having to deal with it in intermediate steps of the execution. So you bring it, you let the adversary run all the way, and at the end you decide, has the adversary done something they shouldn't have? And in EasyCrypt, that's actually horrendous, because it means that you need to build your simulation regardless of if the adversary is doing something they shouldn't have. And then at the end decide, ooh, I can throw away all that painstaking effort. And so the first thing we do typically is say, okay, I know that in that run, nothing bad has happened. And so I can lift a check. I can insert a check that nothing bad is happening, because I know that if something bad is happening, whatever the adversary does is going to lose anyway. Right? So that's usually one of the first steps we do in an interactive proof, or in a proof for an interactive system, is lift all of the final checks into the oracles the adversary has access to, and change their behavior depending on whether the adversary is behaving badly or not.
But depending on the protocol or functionality at hand, then this aspect of going back and checking whether something illegal has happened, sort of, checking after the fact might be as expensive as trying to mechanize to some extent, albeit not perfectly, the interaction in EasyCrypt somewhat. So if you have to go back and mop up all the things that could have gone wrong and check all of those things, it might be, well, intuitively, I don't know this, but I'm just putting a conjecture here, equally as difficult as almost modeling from the beginning the interaction with all sorts of lists and maps and disasters.
Yeah. So that's exactly what our thoughts at the moment. So with this ongoing effort on AKE, that's exactly our approach, is where we're going to try and deal with it formally and looking forward, so reasoning forward, preventing bad behavior as opposed to allowing it and then punishing it. The main issue is that it gives us a different security notion, right? It's not formally the same security notion, and we'll need to argue that somehow they are actually exactly the same, or they capture the same security property. And that's more of a different.
In the same way I told you that if you were to reduce it from interactive to non-interactive, you have to argue formally somehow that what you end up with. Yeah, okay, fair enough. Well, thank you for a lovely talk. Any more questions? If not, I'm aware now that it's 10 minutes past the hour. Questions? No more questions? Well, thank you very much, François.
If you want the story time, all the story times I missed, and just ping me an email, and I'll be happy to share.
No, I have to ping you an email anyway, about not just one, probably about 10.
I wasn't talking to you, I was talking to everybody.
Yeah, I was joking. Yes, do ping François an email. He's always available for EasyCrypt questions. I tell you that much. Right. Okay, thank you everyone, and see you probably next month. Bye. Bye for now. Bye.